Again, welcome to our first lecture, which is lecture number 1. This is a business calculus, mathematics 200. Our first topic in this course, which is business calculus, we are going to talk about limits. Limit is one of the topics that lead us to derivative. In order to understand the concept of derivative, we have to understand what is a limit. So our main objective here is to find the limit of a function, either they exist or they don't exist. Also to find the limit of polynomial functions, to find the limit of rational functions, and also to find the limit of piecewise defined functions. So what is the concept of a limit? The example is given here. So here we say we have used the notation f at c to indicate the value of function f at x when x equal to c. Again, this is a concept in also in college algebra. So if I have f at 5, we can say that f at x when x equal to 5. So here function is given to f at x equal to x squared minus x minus 6 over x plus 2. Here we know that when x equal to -2, this domain will not exist, or we may say that the function does not exist. Because when x equal to -2, we know any value divided by 0 is undefined. There's no answer. So here we say that we know that x equal to -2 is not the domain of f at x. So f at -2 does not exist, even though f at x exists for every value of x not equal to -2. So even if I have a value -1.99999, the function will exist. It only will not exist when s equal to -2. So this is the graph of the function, the previous. So we can see that when s is -2, actually on the graph we say y is -5. The function is -5. But we can see an open circle. The open circle means again does not exist. The function does not exist. So here we say the open circle indicates that f at -2 does not exist. But it shows that the points near x equal to -2 have a functional values that lie on the line on either side of the open circle. What we're trying to say is that if I have s -1.99999, yes, the function will exist. The function will exist. Again, this is the concept of a limit. We may go more details on it. So, for example, we use the term LIM as the limit. So what we have here, it reads as LIM is limit f at x when s approaches -2. And that will give me -5. Or we can say f at s approaches -5 as s approaches -2. Even f at -2 is not defined. The figure previously shows that when x equal to -2, y approaches -5. We are not going to say y equal to -5, but it approaches -5. So now let's go more detail on the definition of a limit. So here we have LIM, again, stand for limit, f at x when s approaches c equal to L. So this is how we read a limit function. So limit f at x as s approaches c equal to L. We have one-sided limit, and also we have two-sided limit. A one-sided limit can be from the left or from the right. When the limit is from the right, we say s approaches c positive. When the limit is from the left, we say s approaches c negative. So we can see negative and positive at the top of the c. So this means that the value of f, when c the limit from the right, we say s approaches c positive. This means x should be greater than c, or s is greater than c, sorry, s is greater than c. Now, when limit is from the left, it means x is less than c. That's why we say s approaches c negative. The concept of c negative here means s value should be less than, the s value should be less than c, because it's coming from the left. When you draw a line, we know the values on our left are lesser than the value of our right. So when the limit is from the right, c x become more bigger. When it's from the left, s becomes lesser. So following are the two important facts we have to regard on limits. The limit is said to exist only if the following conditions are satisfied. One, limit L is finite value, is a real number. Also, the limit as s approaches c from the left equal to the limit as s approaches c from the right. That is, we must have f at x equal to f at s. When s approaches both negative c and both positive c, they must be equal. So this condition must be met. Sometimes we may have a piecewise function, or a function whereby we have the limit when x is less than c, and also when s is greater than c. When you find both answer and the answer are not the same, it means the limit does not exist. And we may see, again, this is just a theory, we may see an example soon. So one more time, this is the two conditions that we have to know for a limit to exist. A limit L is a finite value, a real number. Also, a limit as s approaches c from left should be equal to the limit as s approaches c from the right. Also, the limit of a function as s approaches c is independent of the value of the function at c. Also, when we have a limit f at x as s approaches c exists, it means the value of the function at c may be either the same as the limit, it can also be undefined, or it can also be defined but different from the limit. So let's go through the properties of limit. I think this may give us more clear understanding of what is a limit. So this a property of a limit. Number one is very straightforward. K is a constant value. So for example, if I have a limit 5 as s approaches c, since I don't have no x variable in my function, the answer will be the same constant value. So here we say limit k as s approaches c is equal to k. So if I have a limit 5x as s approaches 2, then it will be 5 times 2, which will be 10. But if I have a limit 5 as s approaches 2, the answer will still be 5 because we don't have a variable x in our function. Then the next one said, if we have limit x as s approaches c, here remember we have only a variable x. So whatever s approaches, whatever the value c is, that will be our answer. So let's say if I have limit x as s approaches 2, my answer will be 2 because the function is only x. Now, if we have two functions, either they are adding or subtracting. So let's say we have a function f at x and also g at x. And we can either add them or subtract them. So f at x plus g at x, or f at x minus g at x. So if f at x is L and g at x is m, then it will be L plus m or L minus m. Here, the condition is given to us here that g at s equal to m. M can be any value. And also f at s equal to L. L can be any value. Now, if I have a limit as s approaches c, f at x multiplied by g at x, then I multiply the two functions. So we multiply L and m. Here again, we are assuming f at x is L, g at x is m. So it will be L times m. The same thing, we have a limit s approaches c. This time we have f at x divided by g at x. So it will be L divided by n, as far as m is not equal to 0. If m is 0, then again, it's undefined. Here also we have a limit s approaches c, square root or root of n, f at x, root of n. So here we look for c, value is x, s approaches c. So we substitute x with c. And since we know the value of f at x is L, we can say that again, everything is square root of, root n of L. Now, if I have a question with c is a value, let's say 2, then I'll substitute 2 in the function f at x. Then we find the root of n. But here, why we say L? Because we already assuming that limit s approaches c, f at s equal to L is equal to L. Limit f at s, s approaches c is equal to L. So we have limit s approaches c, f at s is L, then root n. We also have a polynomial function. And we may see again an example soon. So if f is a polynomial function, then the property 1 to 4 imply that limit f at s as s approaches c can be found by evaluating f at c. And we may see how that works. So this is again polynomial function. Our first goal here, if we have a polynomial function, we may try to simplify it before we substitute the c for it. And we can use any of the properties from the previous properties we saw. The same thing if we have rational. We can substitute, simplify f at s over g at x. Then whatever solution is, we substitute c to x variable. So here we have f at c divided by g at c. Okay, now we went through, spent a lot of time on the theory. Now let's do the practicals now. I think this is more examples. So the following limit, we are going to find it. We're going to find again the following limits. So here with first question, we have limit x approaches -1, s cubed minus 2x. Limit s approaches 4, s squared minus 4s over s minus 2. Sometimes so we can say limit s squared minus 4x divided by s minus 2 as s approaches 4. So let's solve the first one. First one, if you like, we can simplify it, or we can go ahead and substitute x with -1, which means we are going to find f at -1. So here we can see we have -1 cubed minus 2 -1, and that will give us 1. We get -1 plus 2, and 2 minus 1 is 1. Either way, we can substitute this. For example, s is common, I'll take s out, I'll get s squared minus 2. And when you substitute -1 on x, parenthesis s squared minus 2, you will still get 1 on the left side, and then +2, -1, +2. So you still get 1. And 1 multiplied by everything, because we have x outside, we still get the same answer. So this is the function for it, and we can see that again, the limit exists. When -1, we have y or f at x to be 1. Note that this limit has the form, which is division. We have f at x divided by g at x as s approaches c. Our goal is that we make sure g at c should not equal to 0. So let's see this example. So this is our question now. S squared minus 4s over s minus 2 as s approaches 4. So I'm going to substitute 4 at x anywhere I see x. So I'll get x squared will be 4 squared. X will be 4. 4s will be 4 times 4. So let's simplify this. We get 16 minus 16, and 4 minus 2 is 2. 16 minus 16 is 0. So our answer will be 0. And this is the function. So we can see when x is 4, again, f at x is 0. So now we have another few rules here, which we will go through. So sometimes when we have a rational expression, when this result is 0 divided by 0, it means we can simplify the expression more, reduce the expression. When the result is 0, any value by 0, we know it's undefined. So here we say we have seen that we can use property 5 to find the limit of a rational function f at s divided by g at, as long as the denominator is not 0. If it's 0, again, it's undefined. Now, if the limit of the denominator of f at x by g at s is 0, then there are two possible causes. Rational functions evaluating limits of the form f at s over g at x when s approaches c, where limit s approaches c, g at s equal to 0. So we have two forms here, the type 1 and type 2. Type 1 means if the function is equal to 0 and g at s equal to 0, we have 0 by 0, which we call the indeterminate form. This means we can reduce the expression. Now, if we have f at s not equal to 0, but g at s is, then it does not exist. As we said earlier, we can't divide. So these are the two things we have to consider. The previous example was very straightforward. We substitute our value, the value that s approaches. Let's go back one. This is very straightforward. So first, if I substitute these values, 4 with all the x's, and I get 0 over 0, that means maybe I can be able to simplify this expression. But if I get a value divided by 0, it means it does not exist. But in this case, we have 0 over 2, which is, we know this answer, which is 0. So now let's see an example here. So here we have x squared plus 3x plus 2 divided by x minus 1. We want to know if the limit exists. So first we substitute 1. And what we get here, we get 0. And we substitute 1 through this, we get 1 plus 3 plus 2. So by substitute 1 for x in the function, we get 6 over 0. So this limit has the form a can be any value by 0. When a is not equal to 0, then it's type 2. So this means, again, the limit does not exist. We cannot divide numerator and denominator, or numerator by 0. So again, this means the limit does not exist if we have any value divided by 0. Now, let's see this example here. So here we have x squared plus 1 when s is less than or equal to 1. S plus 2 when s greater than 1. This is called a piecewise function. Now, for the limit to exist in this piecewise function, it means the answer for s squared plus 1 when s is less than or equal to 1 should be the same as s plus 2 when s is greater than 1. So let's solve it. We solve the first one again. Since it's less than or equal to 1, we are assuming 1 negative. Again, we substitute 1 plus 1. 1 squared is 1, 1 plus 1 is 2. Now we take the second one, which is greater than 1. So it's 1 positive. We get 3, no. So, which means 2 is not equal to 3. The limit does not exist. 2 is not equal to 3, so the limit does not exist. And this is an example of it. Plotting it, we can see that as we get closer to the value, we can see we're getting closer to 2. But we can see from here, from the graph, it doesn't exist when it's 1. Let's open interval. Now let's try the second one. So we see how a piecewise function is. So we have two equations, but remember their approaches must be the same value, either to the left or right, less than or equal to 1, greater than 1. I cannot say less than or equal to 1, greater than 2. They have to be same, then we have piecewise function. And so we saw another one. We had a value divided by 0, which means the limit does not exist. When we have a piecewise function, both function can be 2, 3, can be any amount. Their answers have to be the same. If they are not the same, they also does not exist. So now let's try this function here. We plug in the 2, and this is using the sum and difference property. So we can see that we have 2 squared plus 2 times 2 minus 3. And our answer will give us 5. So we separate it, but sometimes we don't need to separate it. I just plug the 2 here, 2 squared plus 2 times 2, that will give me 2 squared, 8, 8 minus 3 is 5. But the property said we should separate them, so we get limit s squared s approaches to plus, limit 2s s approaches to minus, limit 3s approaches to. So limit s squared s approaches to will be 2 times 2 squared. This will be 2 times 2. This will be constant value, so it's the same 3. And the answer is 5. So again, this is our question. The goal here is that we should substitute the 2 to anywhere we see x and solve it. Now let's try this example here. We have 1. So the first thing I'm going to do is substitute 1 anywhere I see x. So I have 1 cubed minus 1 will be 0. 1 minus 1 will be 0. And remember, we said that when we have 0 by 0, which we call indeterminate, it means we can reduce maybe the expression. If I have any value divided by 0, it means the limit does not exist. The limit does not exist. But in this case, we will try to reduce it. And then we see that we have an algebraic formula here, s cubed minus 1 cubed. So we can break it down. Remember, s cubed minus 1 in college algebra is the same as what? X minus 1 times s squared plus x and 1, but since it's 1, we say only x plus the b, which is 1 again. B is 1 square, but it's 1 square is 1. So s cubed minus 1 is the same as s minus 1 times s squared plus x plus 1. Okay, here we see something. We can cancel s minus 1, s minus 1. Then we reduce it down. So we get s squared plus s plus 1 now. So we can try to solve the limit now. So we substitute 1, square is 1, 1 is 1 and 1, so the answer will be 3. So s cubed minus 1 divided by s minus 1 is the same as s squared plus s plus 1. When we simplify the top, as we can see it here. S minus 1 cancel s minus 1. So we get s squared plus s plus 1. So let's try this next one, find the limit. Remember here we have rational expression here, but again, let's plug in the value and see what we get first. When we get any value divided by 0, the limit does not exist. If we get 0 divided by 0, then the limit exists, but we have to simplify the expression. So we put in 0, and I get square root of 1. Square root of 1 is 1. 1 minus 1 is 0. The down I have only x at the denominator, so 0 over 0. Okay, this means we can simplify this expression. So we can find a rationalize. So what I'm going to do is that if we remember college algebra, I want to remove the square root. So in order to remove a square root here, I have to do something we call the difference of 2 squares. Difference of 2 squares means if I have a square minus b square is the same as what? A plus b times a minus b. Then that's what I will do here. So I will look for square root of s plus 1 plus 1. So square root of s plus 1 minus 1 times square root of s plus 1 plus 1. We have difference of two squares now. So the answer will be s plus 1 square root all square minus 1 square. And that will remove the square root. Square and square root cancel. Then remember the down also we are going to get, since we multiply the top by square root of s plus 1 plus 1, we're going to multiply x by s square root of s plus 1 plus 1. So let's see how the expression works. Here we say the direct substitution fails. Why the direct substitution fails? Because we get 0 over 0. The numerator is 0, the denominator is 0, which tells us that, again, there's a possible way of reducing the expression to get a solution. But again, if it's any value divided by 0, that means no, the limit does not exist, no solution. So that's what I'm saying now. We have square root of s plus 1 minus 1 by x. That's our original expression. But we're trying to remove the radical sign. So minus 1 turned to plus 1. So this gives us a difference of two squares. So we get a square root s plus 1 all square minus 1 square. So we can see the square root is gone because square root and square will cancel. Now we will try to solve this question now, if possible. So s plus 1 minus 1, remember s minus 1 is what? Is 0. And s can cancel, s is 1. So we get 1 over square root of s plus 1 plus 1. Now we can do our substitution with a 0. So we can see our answer will be 1. Sorry, 2, half. We get 1 over square root of 0 plus 1 plus 1. So square root of 1 is 1. 1 plus 1 is 2. So we get 1 over 2. So the solution will be half. Again, those are the basic concepts. The homework assignment, these are the concepts we are going to use. As we said earlier, there are 3 ways. You can see this is the question, but I know, or we know that when we substitute 0, we get 0 over 0. Okay, if it's 0 over 0, then we have to simplify the expression. If it's any value by 0, the limit does not exist. Also, piecewise, if all the functions have the same value, limit exists. If all the functions have different values, or even if it's 3 functions, 2 have the same value, 1 doesn't have different value, the limit does not exist. All the functions in the piecewise function, they all must have the same value. So this is another example. We can see here, I have -5. So I'll do a direct substitution here. -5 squared will give me what? Positive 25. 25 over 25 is what? 0. Now let's try it down here. -5 squared will give me what? 25 again. And here we get -5. That will give me -10. So 25 minus 10 is what? 15. 15 minus 15 is what? 0. So this expression, if I do a direct substitution, I'll get 0 over 0. Okay, then we need to find a way to simplify it. Again, I'm repeating it. If you get 0 over 0, you have to simplify the expression. There's a solution. But if you get any value divided by 0, there's no solution. And also piecewise, if all the values are the same, there's a solution. If the values are not the same, there's no solution. So these are the few common concepts we should get in the limit. So I see this is a difference of 2 squares. Okay, so this is a difference of 2 squares. So what we get is that it's s squared minus 25, s squared plus 2s minus 15. If we substitute 5, -5, we will get 0 over 0 because -5 squared is 25. 25 minus 25 is 0. -5 squared is what? 25 again. 2 times negative 5 is negative 10. So that will give me positive 15. 15 minus 15 is 0. So here we use the difference of 2 square. S square minus 5 square. So we get S square minus 5, S plus 5. This looks like a perfect square because I'll get two values. 2 times 5 is 15. The difference of it is 2, but it's negative 15. So we get positive 5 and negative 3. That will give me negative 15. Then combining negative 3 and 5, that will give me positive 2. So that gives it S minus 3, S plus 5. Again, what I'm doing here is I'm factorizing the expression. If you have a question on this, the Mathematics 164 pre-calculus, I also have a video on how to factorize equations. So we factorize this, this is what we get. Then I think we can cancel something. S plus 5 will cancel S plus 5. So we get S minus 5 over S minus 2. Now let's substitute the negative 5. Negative 5, negative 5, that will give us negative 10 over negative 8. And 2 will go into 10 will be 5. 2 will go into 8 will be 4. So the answer will be 5 by 4. Another example here, again, since this is a polynomial function with no denominator or rational, it's not a rational function. Let's try the direct substitution may work. Most of the time it works. So we get 8 minus 3 times 2 plus 12, 2 squared, 4. So we get the answer to be 50. And another example given us here. First of all, we try to substitute the negative 3. So I'll get negative 6 plus 22 will give me 16. Square root of 16 will give me 4. So 4 minus 4 is 0. Negative 3 and negative positive 3 will get. So here I'll get 0 over 0. So again, we have a square root. So I'm going to do the previous example we saw. I'm going to use difference of 2 square, remove the square root. So we get 2s plus 22 plus 4 because this is minus 4. So we use plus 4. We use the same down. Then the square root will be gone. Minus 4 square will give me 16. Multiply by everything down here. Here also we can simplify. 22 minus 16 will give me, I think, 6. Then 2s plus 6, 2 can be common, then we get s plus 3. We cancel s plus 3, s plus 3. Then we substitute negative 3 to the rest of the function here. Our answer will be 2, 8 and 1/4. Same question apply here. I can see that the same thing here. I will get 0 and we also get 0 here. So we have to factorize the trinomial and also the same thing down. We also have an absolute function here. So when we have absolute function, remember absolute function, whether it's positive or negative, the answer always will be positive. So first, we are assuming this is 10 minus s minus 5. So we solve the expression, we get 10. Then we use the positive one. Again, this is absolute, so assuming this is negative value and positive. So we solve the negative aspect of it to give us 10. Now we change it to positive also. The answer also the same thing, 10. Okay, if both are 10, that means the limit exists and the answer will be 10. So remember, absolute, because we have what? Greater or less. It's approaching 5, so it can be approaches 5 negative, that's from left, approaches 5 positive from the right, which is if s is less than 5 or s is greater than 5. When we do both, we get the same value. Less than 5 means in front of the absolute value will be negative. Greater than 5 means the absolute value will be positive. So we solve it, we get 10. Again, thank you for this short lectures, and I wish to see you guys in the second lectures. If you have any question, again, send an email to me, And also you can subscribe my channel or comment, or if you like it also, that is great.